Quick. Prime factorize 3599 and I will be giving you just 5 seconds to do that. Okay, time's up and you're wrong unless you were right. So let's say you have to factorize some other number, prime factorize it. Let's say 91. What you might be doing is you might be looking through a series of prime factors that actually can divide 91. So 2 does not divide it because it does not have an even digit. 3 does not divide it. 5 does not divide it. 7 looks like that. So it is just 7 times 13. But if you did that on this, then it might have taken you a while. The key here is to think that this is 3600 minus 1, which is just 60 squared minus 1 squared, which is just 60 plus 1, 61, multiplied by 60 minus 1, 59. And you can recognize them because they are prime numbers. But did you feel the beauty of this step? The step that joins the difference of squares of two terms to the sum, to the product of their sum and the difference. And although there is a very nice algebraic proof for that, which goes somewhat like this, it does not give you much intuition because you start with some well-known algebraic identity and you go ahead and derive it. But what I am here to do is give you the intuition of why this is true. So for that I'll be using two squares, really. Whenever we think of something like a squared, we can think of it as measuring the area of a square with side length a. So in this case we have a square of side length a, and their areas must be equal to each other because they are congruent, which means that both of these are squares with side length a and they have the area a squared have the area a squared, so their areas are equal to each other. Now we want to remove another square from it, which is b squared. So let us go ahead and remove a chunk of square here, which I will call b squared, and this has the side length b. Similarly, we will be removing that square over here, b squared, we will be removing that, and in order to remove that we will be cutting that off. So we can cut that off, and I should not use scissors on camera, I'm really bad at it. We can cut that off, and this is the same thing as doing a squared minus b squared. This is the same thing as doing a squared minus b squared, and notice that their areas are still the same because we subtracted the same thing from both the sides. A squared minus b squared from this side and a squared minus b squared from this side as well. So this equality sign holds. Now what I am about to do is try to rearrange this in order to get a shape that we are familiar with. So let me cut this off so that we get a familiar shape, and notice what we have here. We have a rectangle. What about the side lengths of the rectangle? We already mentioned that this was a, this thing is a, and since we cut that off from here, this thing is b. This side length over here is b, which means that we are adding b to this, and we are subtracting that b from this one. So this length right over here is a minus b, and this length, the longer one, is a plus b. So we can go ahead and write that a squared minus b squared is the same thing as the area of this rectangle, or the area of the rectangle with side lengths a plus b, as we derived before, and a minus b. So we can simply write that this is a plus b times a minus b. And notice, when we think of it geometrically, we can visualize it. And that helps to provide visual intuition to us. And if we go ahead and think of some formulas like a plus b the whole squared as the areas of square with a side length of a plus b, then we can get it really easily. So we can go ahead and think of a plus b the whole squared as literally the square of a plus b, and a plus b the whole cube as literally the volume of the cube with side lengths a plus b. And that gives us really good intuition. So whenever you use this formula a squared minus b squared, don't forget that it has a really beautiful underlying geometry that deals with all kinds of symmetry, just like this.